what kind of information we can draw from that. The backgrounds of these slides, thanks to the most wonderful elements of dialing class from Bob. I have a few examples that are of my favorites. This the NBS Sundial happens to have both the style and the Nodus, which is great. And while point shadows give you richer data, they introduce unique geometric, optical, and safety challenges. And they're looking around, there are a number of examples in this room of the safety challenge. And rather than picking on any of them, I thought, well, there's a perfectly anonymous example at the back of the room. Conveniently red-stained fruit skewer. There's your safety challenge. So of course the polar style gives you the nice 15°/hour line shadow. The trade-off being it completely disregards date information. And moving on to the Nodus, it speaks two languages. We have both the hour angle and the solar declination encoded by that point shadow. And the point can be a tip, a notch, a ball, or a hole. And it's been around for a long time, going back in antiquity. The point shadow isn't anything new. And again here, a very famous sundial in the background that uses the point shadow. The core thesis is that given this dual coordinate reliance on a solitary shadow spot, how does the physical shape and finite size compromise or optimize the accuracy? So the problem, of course, is the penumbra. 32 arc minutes of shadow gradation between dark and light, and we are in the position as the human observer of trying to pick out the true shadow position in the center of that penumbra. Oops, hit the wrong button. Well, oh, there's your last bingo card. I've never met him. How do I turn off that? Oh, never mind.
Hit the bottom.
Okay, there we go. I've never met him, I've interacted with him, but I'm sure, I understand most of you probably have.
Yeah.
Back in 2006, John put together this delightful little experiment and concluded that the cone and the blunt conical tip gnomon were the best of all of these examples. And it turns out that's consistent with what I'm going to propose here. The whole idea is that we're shifting from trying to eliminate the blur, although I guess we could, there's been attempts at eliminating the blur. Rather than eliminate the blur, let's structure it so that we minimize that region of uncertainty caused by the blur. And if you take a soft shadow intersected with another soft shadow, two regions of uncertainty, intersect them at 90 degrees, you conveniently have reduced that area of uncertainty to a square. A point, on the other hand, makes that region of uncertainty much, much larger, and therefore there's my thesis that 90-degree intersection gives you the optimum point shadow, and as well as a much safer situation than a needle.
Is the cord on the ground and has to get plugged into the computer?
It was plugged in. Why is it?
Was this?
No, it's been pulled out.
It just flashed plugged in and now it unflashed, so.
Okay. So the cube vertex gives you this ultimate shadow intersection. You could take it even a little bit more ridiculous and actually rotate that cube around the point of the gnomon to follow the sun to always give you that 90-degree intersection on the flat surface throughout the day. But it's a matter of diminishing returns. It's approximately 90 degrees. You can get pretty far away from that and still have your square becomes a diamond, which is still pretty easy for the human to pick a center point. So the manufacturing advantage of a cube is great. I have a bunch of aluminum and walnut cubes that I've made for various temporary sundials, and it's a really nice, convenient Nodus, gnomon. Here's an example of, and in the process of image reproduction to this slide, it actually is reducing the effect of what I have observed. So I encourage you to try this on your own, but it's much easier. It's much easier to visually interpolate this in the intersection of two fuzzy lines than it is here. And in fact, this is one of my walnut gnomons and the nail. Great example. Try it at home, it's fun. It's a great example of how that 90-degree intersection gives you a much better result than a sharp intersection. It happened that a little while later some clouds came up and it further illustrated, and again, much more than this slide shows, the nail shadow was virtually impossible to resolve to a point, but you could still pretty much do a decent job of, you can still do a pretty decent job of identifying that intersection of those two fuzzy lines. Now, there's another problem that illustrated by this graph. If you take, I had previous version, I had all these equations for this, and I should have left them in. Fred, I'm sorry. In the paper that I promised to write, I'll put them back in. This red line represents the mathematical integration of a disk, illuminated disk, progressively exposed by a hard line, i.e. a sunrise. So as the sunrise, you have first a little slit, the shadow gradually comes off, and then it straightens out, and then the last little slit of the sunrise, it slows down again. And of course, the midpoint is what all of our dials and dial software are kind of our designed and designed such that center point is what we humans have to pick out from that fuzzy shadow. If the sun were a point instead of a disk, nothing would have to change in the sundials because they already assume that point source. It's the fuzziness just makes it harder for us to read them. However, I went, I got my master's degree while I was working at Hewlett-Packard in imaging science and working on sundial cameras and scanners, trying to take the spectral radiation off of an object and come up with how the human perceives the three-dimensionality of color and brightness. And this curve represents the psychometric brightness. That is what we actually see that gradation to be. A photodiode or a photon counter sees this curve exactly, but our eyes have this very, very large dynamic range from candlelight to sunlight in the desert. In order for us to do that, we have to compress a lot, and it's all compressed on the light end, giving us the ability to see detail in moonlight. Very obvious advantage for the species. But what that effectively does is moves our interpretation of that halfway point in the penumbra way off of center. So that difference is huge. Now point is actually creating a shadow that we're interpreting over here instead of here, which the design has us in. And so that difference can be pretty big. Our penumbra in the latitudes and temperate latitudes around here are like 2 to 3 minutes wide. That penumbra gets wider as you go up 5 minutes in the northern latitude, even above 15 minutes in the extreme towards the pole. So it turns out it's a pretty significant, that comes out to be a pretty significant error. Considerably more than, for example, refraction at the sunrise and sunset. Well, next year I hope to present a new talk on fully analyzing that situation and treating it and adding that correction in my software. One more problem, these cubes, they're great, they're really nice, they're easy to make, but if you want, as you know, if you want to make your sundial readable, you want to avoid the scrunching of all these hour lines at the summer solstice. So a convenient way to do that is to incline the dial to spread them back out. Well, as soon as you do that, this block has to move toward the equinox, and then you've covered up a bunch of your lines, and it's no longer a useful dial. But it's a case of diminishing returns. You don't really need to go all the way to a polar dial. Just get close, and you get those lines spreading out, so you have more readable resolution. And so what you really want to do is move that block or incline the dial until that block just touches, giving you the maximum readable dial without covering any of it. So what I've done on my software is I've got you can enter your exact inclination you want, but there's a drop down that has horizontal, vertical, polar, and then 2 more, Cancer and Capricorn. And if you pick, for example, Cancer inclination, it puts that right there at the edge. And it turns out there's some non-trivial math to do this, because as you begin to decline the dial, the actual incline has to change to keep that right at that point. So here you can see the incline started at 17.1 for a non-declined dial, and then 18.3 for south-southeast, 32 for east-southeast. But now setting that to Cancer on the software, I've automated that. And again, I'll come up, there's a nice equation for that, and I will publish it and put it in the commit and submit it for acceptance in the compendium.
You heard that.
So there it is, that's the end. So when it comes to designing the perfect sundial, don't get hung up on the point. Remember, it's hip to be square. And the takeaway is simple. If you want your gnomon to be sharp, you actually need it to be a little blunt. Thank you.
Thank you.
Yeah.